Section 14.8 is about the Lagrange multipliers method. Lagrange multipliers method is just a different way of finding or optimizing the function of several variables subject to a constraint equation. In other words, how would you find the maximum minimum value of a function of several variables? Like in this case, let's take it like two variables subject to limitation or the constraint equation that you have a g of x y is equal to k is a constant. In other words, geometrically, it means what? If you would have drawn this level curves of the original function, which happens to be these guys, these are the level curves. In other words, if I would have set the function equal to c and choose variety values of c, that would generate what? Bunch of curves, and those are called level curves, correct? But I'm not trying to find the relative max or minimum or optimum value of this function where the sky is limit. So you have to give me some sort of limitation. In other words, what are my restrictions? And this is what we call subjective function, which is pretty much your restriction. You have to, or I have to, find the optimum value of this function subject to the fact that this equation is true. In other words, I'm trying to find the absolute, well, let's say, extrema values of this on this, on coinciding with what? With this specific level curve. Suppose I graph that specific level curve here, which I'm going to show it with the dotted line. If I stand on a random point on the level, constraint curve, that's what it's called, constraint, is that right? Constraint curve, and move around. So specifically, if I move what? Towards what? The direction where the function increases, what happens is the function is going to increase till I get to the point P, where the level curve of the original function is tangent to the what? Constraint curve. At that point, their normals happens to be pointing in the same direction. Either they go same direction, or they could be what? Opposite direction of each other, resulting in maximum or minimum value of the function itself. In other words, regardless of which way these guys point out, what happens is they are going to be parallel. In other words, these normal lines to the levels curves and the constraint curve at some point they're going to be normal, parallel. So from chapter 12, we learned two curves, two vectors are said to be parallel if they are a scalar multiple of each other. So this would be the normal line. This is like a normal vector to the what? To the level curves. This is like the normal vector to the what? Constraint curves. And lambda is the scalar. So that's the Greek letter lambda. Okay. So the idea is if you solve the resultant equations from this equation, that would give you the same critical points that what the d-test gave us in 14.7. So back to this guy, at the point of tangency of what? Level curve and the constraint curve, notice these vectors are perpendicular to what? They both perpendicular to the tangent line, tangent vector. Do you see it? So they share what? The same tangent, and they're perpendicular to the same tangent vector, so they must be parallel. They must be either, pointing in the same direction or opposite direction, as I mentioned a little bit earlier. So what happens, back to this point Q, as you get closer and closer to this point of tangency, then if you go left or right of this point P, then the what function doesn't increase furthermore, because the closer you get, the faster, or uh, the the faster the increase of the function f. But if you just go to the left or the right side, it doesn't put any dent in the rate of the change anymore. So turns out this point, Mr. Lagrange discovered that at the point of tangency of the level curves and the constraint curves, you have the what? The optimum value. And that happens when the normal lines to both curves happens to be parallel. Okay? So this is called Lagrange equation, which is gradient of what? The function which is going to be optimized times equals lambda, the gradient of the function which needs to be what? Which is given as our limitation or constraint equation. Keep in mind the order matters. The function which is going to be what? Optimized, that means the function you're trying to find its minimum or maximum has to go on the left, and lambda, scalar multiple of the what? Constraint equation, which is this guy, has to go on the right. So in other words, lambda goes with the constraint equation. The function which we're trying to optimize it does not have any lambda attached to it. Okay, with that introduction, let's go back to this equation, which problem, which we solved a while back in previous section. Remember, the question was find the point on the plane that is closest to this point. You know, find the point on this plane that is closest to this point. In other words, we're trying to find the distance between this point and this plane, and we like to minimize it. In other words, we're trying to find the shortest distance. Okay, remember we did this by using what? Projection method in earlier chapter, and in 14.7, the previous section, I did it by the d-test. If you remember, in this case, this is to be minimized. D was a square root of what? O x minus 0 squared, what? Y minus 1 squared, and then z minus what? 2, is it? 1 squared. Is that right? So that would be like 1, right? So remember we said when it comes to distance type of problems, usually people what? Minimize the d squared so we don't have to deal with what? The radical. However, even though these guys give you the same critical values, but when it comes to actually finding the minimum distance, I have to go back to the original distance formula, not this guy. This is just to make the computation a bit simpler. So you remember what we did. We took the partial derivatives of this objective function, but before we did that, we made sure the function which is going to be optimized is in terms of 2 variables. Remember, the d-test does not apply for function of 3 variables. It's only 2 variables, right? Excuse me. So what do? Right here, I go back, if you remember, I replace the z with this expression, which is the equation of the plane, 2 minus 1/3 of x plus 2/3 of y. Do you see it? So now that I have the optimal or so-called objective function, that's what this guy is called, objective function in terms of 2 variables. Now I can apply the d-test. That results, you know, take the partial, set it equal to 0. That kind of what? Gives me critical values. And then that kind of results in system of equations, and solving this gives me critical values or critical points, right? Critical points or point. And then I can take those critical points and go back to the distance formula and find the minimum distance, which we computed last time, and it was 5 square root of 14 over 14. Now the question is, how would you do the same problem using the Lagrange multipliers? Well, remember, the objective function is this. This is the capital D is what we're trying to minimize. But the subjective function, and it's subject to, or what we call constraint equation, is the equation of the plane. In other words, I don't want just any point in the space. I only want the points on this plane, which happens to be equal to the shortest distance to this point, which is off the plane, correct? So according to Lagrange multipliers equation, you take the gradient of the what? Objective function and set it equal to lambda times what? The subjective function. In other words, you're trying to minimize this subject to the points which you're trying to come up with has to be on what? Equation of the plane. Remember, this is the same as what? Z. So if you take the what? Gradient of D, which happens to be what? Right here. This is your D. There it is. Equals lambda times gradient of this function. And the gradient of that function is this vector. Now, you got a vector on the left side and a vector on the right side. When you distribute the lambda, so two vectors are said to be equal if the corresponding what components match. What does that mean? That means I have to set 2x equal to 1/3 of lambda, 2 times y minus 1 equal to negative 2/3 of lambda, and 2 times z minus 1 equals to 1 times lambda. But wait a minute. I have 3 equations, but 4 unknowns, namely x and y and z and lambda. So I need one more equation. Usually what we do to complete the system, we also attach the constraint equation, which in this case was the equation of the plane. So now we have 4 equations and 4 unknowns. Remember, the fourth equation is the equation of the constraint. Yes, yes. So now the question is sometimes students go, well, okay, I set this up. How do I solve it? Well, you set equations 1 and 2 together equal to each other. You get something like this. 2x plus y is equal to 1. Now you take equation 2 and 3, set it equal to each other. You get something like this. So from equation number 4, if you solve it for x, that would be 1 minus y over 2. Equation number, what's that, 5. You solve it for z, you get what? 5 minus 3y over 2. Substitute what? 5 and 6 into 4. In other words, wherever you see x, replace it with 1 minus y over 2. Wherever you see z, replace it with 5 minus 3y over 2, and keep the y's the same. So now you have a function of single variable function equation. So one equation, one unknown. I think we should be able to solve that for y. Well, what do you know? When you solve for y will be what? 2 over 17. From equation number 5, you can find what? Let's say z, x, and from equation number 6, you can find z. So the critical points are what? 5 over 14, 2 over 17, and 29 over 14. Well, what do you know? That coincides with exactly the critical point which we had when we used the d-test. Do you see it? So as you can tell, even though the computations are a little bit busy work, tedious, but if you be patient and kind of, stick with it, at the end of the day, you get the same critical points as you did when you applied the d-test. So the question is, well, if I could have done this problem with the d-test, expressing the optimum objective function in 2 variables and apply the d-test and get the same answer as Lagrange multiplier gave me. So what's so good about the Lagrange multiplier? Well, that's a legit question, right? So I'm going to do two examples. I'm going to show you two examples, and hopefully that will explain why we use Lagrange multipliers. Suppose you were asked to find the maximum minimum value of, let's say, oh, let's see now. Okay, let's do this. Suppose we were asked to find the maximum volume of a rectangular box with the surface area of 64 cubic centimeter, square centimeter, excuse me, square centimeter. So you see what the problem is, don't you? This is a square centimeter. In other words, give me the dimension of a box with maximum volume, but the surface area is fixed. In other words, the surface area, I want it to be 64 square centimeter. And it's a closed box, meaning it has a lid on top. So what we're trying to do is maximize what? The volume, which is length times width times height, so to be maximized. But there is a limitation. The limitation is the surface area has to be what? 64 centimeters square. How do you find the surface area? You have to find the area of these 6 sides, which happens to be 2xy plus 2xz plus 3yz equals 64. So notice I have a multivariable function, and z is all over the place. So instead of solving this guy for z and substitute it here and using the d-test, I don't have to do any of that in Lagrange multipliers anymore. Why? All I have to do is form this equation, which is gradient of what? Of objective function, okay, equals lambda times gradient of subjective function. Subjective function. Do you see how the order goes? All right. So if you take the gradient of v is equal to xyz, you get this, equals lambda gradient of this guy equals this. Now you distribute the lambda first on the right side, and then set each corresponding components of what the vectors on either side equal to each other. Do you see it? Okay, like so. But don't forget, you got to distribute the lambda first. When you do, you get these three equations. But then again, you got three equations for unknowns. So what we do, we usually augment or attach the what? Constraint equation, which in this case happens to be what? Equation of the surface area, which is 64 square centimeter. It's fixed number. Then again, from equation number 1, there are many ways to solve these. Here is a way to solve it. Solve this guy for lambda, solve this guy for lambda, solve number 3 for lambda, set 1 and 2 equal to 0 to get rid of the lambdas, and that in turns gives you this equation. These guys are like terms, they disappear. So move this guy over and factor out 2z squared, you get this. So the product of two factors is equal to 0. Either of those factors have to be equal to 0. Either 2z squared equals 0 or y minus x equals 0. Z cannot be equal to 0 because if it is 0, you don't have a box. So what? Y minus x has to be equal to 0, which that in turns means y is equal to x. On the other hand, if you set equations 2 and 3 equal to each other, you almost get the same what? Equation. In this case, when you factor out 2x squared inside the parentheses, you get z minus 1. So either 2x squared equals 0, which means x is equal to 0, but that's not possible because if x is 0, there is no box. So in that case, z minus y has to be 0, which means z has to be equal to y. Substitute 4 and 5 into what? Let's call this guy, sorry, let's call this 5 and 6. So substitute 5 and 6 into 4, and lo and behold, you get this. So replace the what? Y's with x, replace the z's with y, but y is the same as x, so you get this. So you get 6x squared equals 64. So when you solve for x, you get 8 over square root of 6, which is the same as y, which is the same as what? Z. So the maximum volume is 8 over square root of 6 cubic centimeter. Notice in this case, the box is a what? A cubic box. You see it because the dimensions came up to be the same. On the other hand, sometimes you may have this equation, this problem. Find the maximum minimum volume of a rectangular box whose surface area is 15 square centimeter and whose total edge length is equal to 200 centimeter. So now you have two constraints. So did you notice why we used the Lagrange in the previous problem? It was really kind of tricky to solve this for z and substitute here and get a mess, whereas Lagrange multiplier did not care about what? Solving this guy for z, nor it cared about what? Expressing the objective function in two variables. It could be any number of variables. So that's benefit number one. Benefit number two is this. What if I got more than one constraint equation? In other words, what if I have two different set of limitation for the same problem, which I'm trying to find the optimum value for? In this case, just like before, we're trying to optimize the volume. In other words, find either relative max or mean, or absolute max or mean, I should say. So this is the objective function. But subjective functions, as you can tell, these are like my limitations. Subjective functions, I have two of those guys. One of them says what? Just like previous problem, the surface area is fixed. And now additional what? Constraint equation is what? The total length of the box, as you go through what? 4 length of each side and add them up, that's equal to 200 centimeter. So what happens is when you form a what? Lagrange multiplier, now you have two so-called Lagrange multipliers. So incidentally, I kind of forgot to mention lambda, and in this case mu, are called Lagrange multipliers. Okay, whereas here lambda was called Lagrange multiplier. So in the definition, the original equation we came up with, this is the what? Objective function, this is the subjective function, and lambda is called Lagrange multiplier. So in this case, guess what? I got two multipliers, lambda and mu. So this is lambda and this is mu, like music. All right, so what I have to do is what? Take the gradient of my volume, set it equal to lambda times the gradient of my surface area plus mu times gradient of the length. In other words, the second benefit of Lagrange multiplier is you can have as many constraint equations as possible, as your heart desires. All you have to do, just add more factors on the right side of this equation. Had I had, let's say, 3 constraint equation, then my equation would look like what? Delta, whatever the function, equals lambda delta, let's say, oh, I don't know, let's say S plus mu delta or del L plus gamma delta something else like H. So as you can tell, the number of constraint equation or limitations are irrelevant when it comes to what? When it comes to Lagrange multipliers, because the more constraint you have, the more factors you will have on the right side. However, when you add more factors and you have what, more than one Lagrange multipliers, then the number of equations exceed. So now you have what? You got to multiply lambda by the gradient of S plus mu times gradient of the what? Length. And incidentally, the reason I came up with 1, 1 as opposed to 4, 4, 4, because I divided both sides by 4, I came up x plus y plus z minus 50 is equal to 0. And here I divided both sides by 2. I came up with xy plus yz plus xz minus 750 is equal to 0. So these are called level what? Surfaces. Okay, level surfaces. It would be a good idea to set this guy equal to 0 before you take its gradient. So notice I have now 5 equations, 5 unknowns. 3 of them come from here. The remaining 2 come from the constraint equations with the I attach. Solving it is kind of like a tedious job, but it is possible. What happened in this case, lambda gives you 2 separate values. In turns, that gives you 2 critical values, one of which gives you minimum volume. The other one, if you take what? The plus sign gives you what? Maximum value. And incidentally, when you solve for x and y and z, you will see that the box is not a cubic box. It's not cube. All right. Hope that gives you an idea how Lagrange multiplier applies and why do we use Lagrange multipliers, even though computations are tedious, but it's really fascinating topic when you have multiple what? Constraint equation, and when the constraint equations are implicit functions. In other words, you can't solve for z anymore. And that's really the benefit of a Lagrange multiplier. Thank you, guys.